All right. So a few lectures ago, we saw the concept of limited direct execution or LDE, right? Where what was the main like philosophy or thing about it? That it was to give the OS some control, and at the same time, it was there to do things efficiently, right? So in LDE, the program runs on CPU, slightly small, directly, right? And but at certain key points, the OS takes over and makes sure that nothing goes wrong, right? So these are the two major things in, as I said, it is efficiency that, like, for the most part, OS stays away. And then there was this notion of control that by so coming in between the process and processor sometimes. So that is also called interposing at the right points. The OS keeps control. Okay, so this was just to, so why am I repeating this about LDE? Because similar thing is going to happen in what we are going to see in today's lecture also. And these things for this OS requires some hardware help as well. Okay. So this we had seen was for virtualizing the CPU, right? Now, today what we are going to do is virtualize the memory. And again, the key principles are going to be what is going to be needed: efficiency and control. Okay, good. So, what is going to be today's like in the questions that in today's lecture we'll be answering? So, so how to build an efficient virtualization of memory? Second is going to be how to make it flexible. We'll see what we. So we would want it to be flexible in terms that we should be able to move it, and it should be still transparent with respect to the process and so on. And how to maintain control over memory accesses by processes. And finally, how to do all this efficiently. Okay. And the answer to these questions, like in short, is going to be the technique, which is called hardware-based address translation, or we'll be just calling it address translation for short. But we'll be talking about the hardware-based implementation of it. Okay, good. So what is this going to be? So using this, the hardware transforms every virtual address into a physical one in any memory access to a physical one. So last time we were talking about, okay, what is virtual address, what is a physical address, and so on. Okay, good. So this happens on each memory access, okay? But the hardware, of course, does not like do it, all by itself. And it's going to, because I mean, this is just hardware provides some low level mechanism, right? Like in last part that, okay, during context switch, the hardware in LD just saved the registers and so on. So it provides low level mechanisms only. So again, like before, the OS needs to intervene at right times. To make sure nothing goes wrong. Okay. And also, part of this is going to be like, OS also has to keep track of which memory location is free, which is not, etc. So we'll see all this in detail. Okay. And as I had emphasized this last time, that why all this is being done? To maintain the illusion of that the program has all the memory to itself. So this is the like most fundamental thing about virtualization of memory. So like just reiterating it. So now we'll start with the actual mechanisms and so on. But before that, we'll make some assumptions which will make things easier for us in this lecture. And then we will relax them as we go. Okay. Okay. Very few people today in the class. Maybe they'll trickle in. All right. So I was saying that we'll be making some assumptions about the memory. And the first assumption is going to be that for a process, all its memory is going to be placed in its address space is going to be placed contiguously. So I filled in the word here contiguously. And second is going to be size of the address space is less than the size of memory. And third, all processors have address spaces of same size. So these are the assumptions for today, and of course they are not going to be like that's not the reality. But to build up and to see the basics of certain things, we'll need these assumptions for today's lecture. Okay. All right. So let's see some examples of how these things will be done, or what kind of support we want to provide. Okay. So let's see. So I need to push it all the way up because I want to draw something big here. So suppose this is the address space of a process. Okay. And then suppose this is 0 KB. Here somewhere is 2 KB. From 2 to 4, let's say there is heap, and from 14 to 16. So let's say that the address space has size 16 KB, and here is the stack, and so this is the stack, this is the heap, this space is free. Yeah. And now suppose at certain locations there is some code, right? So let's say, going by the book's example, that let's say that here at 128th location, 132nd location, and 135 location, let's say there is some code, and that's assembly code. So that, okay, so suppose we wrote a C program, void function and x is equal to 3000, x is equal to x plus 3, Then we do something else. So we just declare an integer and then we increment it by 3. Okay. So this is the line we'll be interested in. X is equal to x plus 3. So suppose the address of x is already stored. So stored in EBX register. Then let's say that the corresponding assembly code for this line is that at 128 it's move L by offset 0 the contents of the address in EBX to, I mean, even if you don't know assembly, maybe some of you don't know, it doesn't matter much. I'll tell what it means and just then at 132, suppose it's add the value 3 to whatever is there in EAX, and at 135 it's move L long, and it is whatever is in EAX you want to put it to whatever the address is in EBX. Okay. So what are these? So this is to so we have assumed that the address is already stored in EBX. So what this instruction does, copy the value at address in EBX to EAX. Okay. So this is for address which is and we offset it by 0. This you can ignore for now. So this is the register EBX, and this means the value at the address which is there in EBX, and we copy that to EAX. Then the second one is just add 3 to EAX, whatever is there in EAX, and this does not have any memory access. And then this says that whatever is in EAX, store it to address in EBX. Okay, so why this kind of code will be performed for this line? Because suppose X is already in the address of X is already in EBX. So then first it wants to load the value of X in EAX before it can perform some operation. So it loads whatever is at the address which is there in EBX to EAX, then adds 3 to EAX, and then moves the value of EAX into the address which is there. Right? Okay, good. So what are the memory operations that are performed? In these 3 instructions. So first, it needs to fetch this instruction at 128. Say address 128 just. Okay. So first it fetches the instruction, which is going to be this instruction. Then it will execute the instruction. And what will executing the instruction amount to? it will amount to load from address. So load from some address, wherever this EBX is pointing to. So EBX is pointing to maybe address of X, wherever X is stored, right? So suppose X is stored here at 15 KB. So here the value of X is stored, which is 3000, right? It will be stored in the stack. So let's say load from address 15 KB. Okay. Now, after this, it will fetch the next instruction. Add address 132. Fourth, execute this instruction. Here there will be no memory access because this instruction involves just taking a register and incrementing it. And then finally the last instruction, which is, so first fetch that instruction. At 135, and sixth is execute instruction, which is going to be store at address 15 KB. Okay. So this is how a program. So whenever you write a program in C, it gets translated to low-level code. So here we are looking at the assembly code of the program. I mean the snippet of the assembly code which corresponds to just these lines. Okay. I mean just this line actually, just one line. All right. So this is how things happen. But for the program, the address space starts at 0 and goes to 16 KB, let's say. And for OS, and the program should generate only the addresses within this limit, of course. And for OS, program is somewhere else in memory. So the question is, how can we relocate a process in memory so that it is transparent to the process, right? In a transparent way. Again, like we discussed, what is transparency in this case? It's not that the program would know everything that is going on, but it's about the program should not be able to see it. So basically, we want to give the illusion of an address space from 0 to 16 KB, right? When the program is actually somewhere else. So how does the OS memory might look like? Let's see. So suppose the OS sits from 0 to 16 KB, then 16 to 32, let's say, is free. So here is the OS sitting. This is free. Then the program actually sits here from 32 to 48 KB. So here is the code. Here's the heap. This is the stack. and this is free. This, but this free is different from that free because this is already allocated to the program. And let's say 48 to 64 is again free. 64 maybe. This is free. So this is where the program decides. Let's say process. And this memory has been allocated to process, but not in use right now. And now, you see that the OS has divided its memory into these, chunks of 16 KB that is going to be the address space. And out of this, like 2 slots are free, which is 16 to 32 KB and 48 to 64 KB. Okay. And the process we wanted considered is at 32 KB. So this is how this is the OS view of the memory, of the actual physical memory, and this is what the process thinks, what its memory looks like. Okay, good. So now, what is this dynamic or hardware-based relocation? Okay, so this is going to be this is also called base and bounce approach. Okay, so also called, as I said, dynamic reallocation. Not reallocation. And there are 2 hardware registers that are needed. One is called the base registers, and the other is called the bounce register. And so they together make sure that using these, the OS would place the process and also make sure no illegal access happens. Okay, good. So how does the base register work? So as I said, the program written as if loaded at address 0. Okay. And when it is about to run, the OS looks for a free slot in the memory and puts it somewhere, right? So OS looks for where to like load it. Okay, and sets the base register to that value. Right. So, for example, in earlier one, if we go to that example, now the program is actually here, right? At 32 KB it starts. So the OS sets the base register at 32 KB. Okay. Now, how does it help in translating? So that is actually very simple. So whenever a memory reference is generated, what will the hardware do? The processor will translate it in the following way. So physical address is equal to virtual address plus base. Whatever is in the base register, right? Good. So by doing this, the hardware will translate every virtual address to a physical one. Okay. So let's look at our previous instruction, for example. So what was it? Move L percent EX to EX. So this, as I said, this wants to load the contents of the address which is there in EBX to EAX. And the PC of the process, the program counter of the process is at 128, the current instruction, right? Okay. So now, first instruction, first thing is going to be the fetch. So the hardware needs to fetch the instruction. At address 128. This is the virtual address. So now it needs to translate this to a physical one. So now it adds the base register. So 16 KB value of base register. So 16 KB is how much? Or sorry, was it 32 KB? It was 32 KB. So it will add 32 KB, whatever its value is. Let's say 32,768. And then it will add 128 to it. Okay. To get whatever. 32,896. Okay. And now it will fetch the instruction from the physical memory, which is at this address. Fetch from here. Okay. Then now, after this, the process also needs to load from the value at address address 15 KB, let's say, which was the again virtual address, and it will add this 15 KB to the base. So the actual physical address is going to be 47 KB. All right. So that's where the process will fetch things from. And this whole process is called, as the name suggests, address translation. Okay, good. And also, if a program has run for a while and then it has stopped, and then the OS can also move it from one place to the other, it is also called dynamic relocation. I'll in a moment talk about it, that how this is done. So these two uh, like mean the same thing, and they'll be used like interchangeably sometimes. Okay, so this was just for the base registers. I haven't really talked about the bounce register. So what is the bounce register for? Any guesses?
If a program doesn't access other processes memory.
Yes. And how can we make sure of that? What should the bounce register contain?
Size of the address space.
Yeah. So yeah, that is one way to do it, that it can contain the size of the address space. So as Arpit said, that this is to check whether the memory reference is legal or within bounds. Right? So since we have assumed all the address spaces to be of the same size, so the bounds register will contain size of address space, which here is going to be 16 KB. 16. So it will always remain the same. It will just have 16 KB. And if a process generates something, a virtual address of value greater than 16 KB, sorry, okay. And yeah, so if a process generates a virtual address which has value greater than 16 KB, the now the OS will compare this with the processor will compare this. This is a hardware level thing. It will compare this with the bounce register, and the CPU will raise an exception. And the process will be terminated. Okay. So these two registers, the base and the bound registers, they are kept on chip. their hardware structure. Kept on the chip, the CPU chip. And these are like basically part of a larger structure that we'll see, which is called the memory management unit. So right now it just consists of these two registers, but we'll see that there will be more things later. Muted it. Okay. So these registers are part of the memory management unit, and this is part of the processor that, as the name suggests, that helps with the address translation and memory related issues. Address translation. So, as I said, right now it just has two registers, but later we'll see that it has more stuff. Cool. So, as I said, the bounce register, not just, I mean, it can have the size of the address space, but it can also contain just the like limit of the physical address space. So as I said here, the bounce register can also contain this value, 48 KB. Okay. So, but they both are logically the same because then what the CPU can do is add the base address to the virtual address and then compare it with the bounce one. And if it is more than that, then it will erase the exception, right? So the bounce register can also contain end of the physical address space. For the process, and logically both things are same. So we will consider the form. All right. So now we know how the at least the basic address translation works. That whenever and that is in this setting. So remember the assumptions that we have made. That first, every process is going to be placed contiguously in the memory. Second is that all the addresses are of the same size, and no, second was that every process address space is smaller than the memory, and the third is going to be that all the addresses are of the same size. Okay. So we have like for these assumptions. So we have just seen the how the hardware support looks like. So this is going to be just base and bound registers. So till now, if we look at what kind of hardware support we have seen, including the previous lectures. So okay, good. So first thing was that the processor had two modes, kernel mode and user mode, right? and there is one bit in the hardware which would indicate this. Okay. And this bit changes in case of an exception or interrupt. Okay. And also the hardware had some like it remembers interrupt handlers, etc. So this was in the last time when we were discussing LD. And today what we saw? Today we saw that in the memory, I mean for memory, there are these two memory registers in the hardware, which are base and bound. And they help, they are part of this thing called memory management unit. Okay, and there is another thing that, of course, the hardware cannot by itself modify the base and bound register. So the hardware should allow OS to modify base and bound registers. And of course, this should only be done in kernel mode. The process should not be able to do this, right? And also the CPU must be able to like raise some exceptions if a process tries to access some like illegal memory access is happening, or if it is trying to change the base and bound registers. So hardware should raise exceptions in cases illegal access or illegal instructions like change base bound or some other illegal instruction. And the CPU should also know how to handle these exceptions. Okay. So, like before, this will be set up by the OS at boot time. Okay, good. Now, so this was the hardware part, that what the hardware does in for the memory translation. So now we, in this whole process, we also need to see that what the OS needs to do, right? So next question is what the OS needs to do. Okay. So the first thing that the OS needs to do is when a process is about to start, it needs to find memory. Okay. So since we have made these two assumptions that address space is smaller then physical memory, and second is that all address spaces are of same size, right? So then OS can view the physical memory as an array of slots, that okay, it is one slot after the other. Each slot has the size which is equal to the address space of any process. So the OS can view the physical memory as array of slots, okay, and then track which one is free, which ones are free, which are not. Good. And the OS generally does this by maintaining this data structure called free list. So this has basically the free slots. And so since all address spaces are of the same size and so on, the OS, like the job of the OS is easy. So like for free list, for example, in the example we had here, this one is free 16 to 32 and then 48 to 64. This one is not free 30 to 48, even though there is some free memory inside, but that does not belong to the OS, that belongs to the process. So in the previous example, this is going to have two slots, which is 32 to 48 KB. And was it 30 to 48? No, it was 16 to 30. And then 32, 48 to 64. Yeah. All right. So we'll also see that what happens in variable sized address spaces and in later lectures. But for today's lecture, let's just assume, as we have said, that the address spaces are going to be of the same size. Okay. So this is one of the jobs of the OS that allocates space. Okay. When a process is going to start running, right? And the second job is going to be deallocate space, right? Deallocate space. So when a process is terminated or exits, right? Then the OS will take back all its memory and put the slot back in the free list, right? And does any other cleanup that is required. So this is when a process is going to start, the first one, and the second one is when a process is going to finish or killed or anything like that. So these are the memory operations that the OS needs to do. And also what happens in case of context switch, right? So we have seen earlier what the OS needs to do in case of context switch for LDE. What more will it need to do now? What is the additional step that is going to happen?
Base and bound register will also be part of the context.
Exactly. They will also be part of the context. And they differ for every process, right? So they differ for every process. And so basically save and restore base and bound registers when OS decides to switch between processes. So in particular, when stopping a process, what those would do, basically save it. So there are some process structures which are like for every process there is a structure which the OS maintains. So base and bound to save base and bound registers to for process structures like so one of them is called just process structure structure or other is called process control block or PCB for short. So the whenever it decides to stop the process, then it will save its current base and bound to this to PCB or to process structure, and when resuming a process, just like the opposite. So it must sets base and bound registers from process structure. Good. Now there is another job that the OS might do, which is moving the process from one physical memory location to another for some reason. Okay, so in this, what the OS will need to do. So first, it will deschedule a process if the process is running. Then it will copy the address space from one place where the process is currently in the physical memory to another place. And finally, it will update the base and bounds register. new ones. I mean, corresponding to the new physical address. Ones corresponding to the new physical address. Okay. And I mean, so, but the base and bound, this process is not currently running. So, base and bound register corresponding to the new physical address to where? To the process structure. So, or in the process structure, not the actual base and bound register, which is like right now. And when the process starts again, then it will load the correct base and bounds. So now the process will run as if nothing has happened. It is because its address space remains the same, its memory references remain the same, and then it is just like going to behave as if nothing has happened, but actually it has moved from one physical location to another, right? So process would not know that it has been. And the final thing that the OS needs to do is exception handlers. So, like before, as we had exception handlers for LTE, similarly, the OS installs these at the boot time. And yeah, so for misbehaving processes, like, which access some memory which is out of bounds, or trying to change base and bound registers, or any such thing, any privileged instructions. So for, as I said, illegal memory access, is also called out of bounds exceptions. Or if a process tries to perform an illegal instruction, then also it will raise an exception, right? So the OS should install these exception handlers at the boot time, and then the hardware remembers their addresses so that whenever those exceptions are raised, the hardware can go to the corresponding instruction and start executing. Right. So this is what has been. So we have extended now limited direct execution to this mechanism called address translation, where the OS and the hardware together control and see that the address which is generated is within bounds. And how does the efficiency comes? Efficiency comes because the address translation is done by the hardware, and it is not by done by the OS, or the OS doesn't have to come in. Okay, and yeah, so there is some wastage of space in this, because as we saw that in between the process there is a lot of space that is not being used by the process, and the OS cannot allot it to something else. So that is called internal fragmentation, and that we'll deal with uh, in the next lecture, or next, we'll see. So just a quick summary, and then we'll see if we can go through the example. Yeah, there is some time. So extended LDE with address translation. And here OS and hardware together control to make sure address is within bounds. Okay. And because of so hardware efficiently translates addresses using base and bound registers. Okay. So one issue, as I said, is internal fragmentation. And we'll see in next lectures. Okay. So now let's just go through one example that the book shows, just to give a clearer idea of what happens at boot time and what happens at runtime, how the control is transferred between the OS hardware and the program. Okay, just to see that how this whole idea of address translation works with LD. Okay, so that's, any questions till now? Whatever I have told.
Are these base and bounds register this address translation not done when it is running in kernel mode?
When it is running in kernel mode. I mean, some basic thing can be done, but generally OS is kept at zero, so base or base is going to be zero, and bound is going to be whatever the OS says thing is. So I mean that it it would be done. Of course, the address needs to be translated, but in kernel mode, it's not that important because the OS should be able to access whatever memory location it wants.
So when a trap is generated to switch to kernel mode, then when like the base and bound register would need to be changed, right? So that the OS
Yeah,
can execute the instructions properly.
exactly.
Right.
So I mean those base and bounds again. So that can be, if that is just part of the OS or it is in the OS's address space, then that base is. I mean, I just gave an example that that can be zero also, and then it can, yeah. But of course, every address that even the OS will do, that will go through, because this is a hardware-based mechanism. So whatever address is being generated, it will get translated to a physical address.
Okay. Good.
Yeah, so I mean, the a short answer can be that yes, they will work even in kernel mode. Okay. So good. Any other question? Okay. So if not, I'll just quickly go through the sort of control transfer diagram that the book has, and maybe I can share it, or no. If I write it, then that will be slower, and maybe you will be able to get like slightly more stuff. So what happens at the boot time? So the interaction is going to be always between OS hardware. So boot time. what happens. So this is OS, this is hardware, and this is user program. So at boot time, of course, no user program runs. So what does the OS do? It initializes the trap table first. And the hardware will remember the location of system call handlers, timer handler, illegal memory access handler, and illegal instruction handler. Okay. So this is what the hardware needs to remember. Then the OS will start the interrupt timer. And then the hardware will start the timer. I mean, the OS will ask the hardware to start the timer. The hardware will start the timer and then will issue an interrupt after every X millisecond. And finally, the OS will initialize process table and free list. So this is what is done at the time of the boot. Okay, this is how the OS and the hardware interact, and there is no user program till then. Now, suppose at runtime, what happens? So, again, OS, hardware, user program. Okay, so suppose the OS is going to run two programs. We'll see what happens. So process A and B, suppose it's going to run one after the other. So to start process A, the OS first allocate an entry in the process table. Allocate some memory. And set base bounds registers, which will correspond to this memory that it has allocated, and then execute the return from trap to A. Okay. Now, after this, it will come to the hardware. What will hardware do? It will restore the registers of A. Move to user mode. And then jump to A's program counter. Right. Now A runs. And let's say there is some fetch instruction which happened. Then what will the hardware do? It will just translate the address of the fetch instruction and fetch it, right? And then the program will execute its instruction. Now, while executing the instruction, now if it is a load or store instruction, depends on like what kind of instruction it is. If it is load store, then see if the address, if it references an address, is legal. If so, execute. Otherwise, raise an exception. So suppose this does not happen, raising exception and A runs. Okay. Then what happens is, suppose then A is running, then timer interrupt happens in the hardware level. Then move to kernel mode. And jump to the handler. Timer handler. Okay. Now it is in kernel mode, so the OS comes into picture. Now the handler for timer comes. Now suppose it decides to stop A, run B. Okay. So then it will call the switch routine. Save registers of A to some process structure of A. Load registers of B. So this will include base bound. Load registers of B from process structure of B. Again, this will also include base bounds. Okay. And then perform return from trap to B. Now restore the registers of B. The hardware will do its job. Move to user mode, just like before. And then jump to B's PC. B runs and again fetch, translate, and now B executes a bad load. So it has like, the address translation goes out of bounds. So then the OS will see that the load is out of bounds. Sorry, the hardware will see and move to kernel mode. Jump to trap handler. And then the OS will handle the trap, decide to kill B, reallocate B's memory, and free B's entry in process step. Okay, so these are the steps that are like involved in some sense. So as you see that if a process is running normally, the OS does not come into the picture. It's just between the so for A, as long as A ran, the OS did not come. So that's why this is efficient, that the OS doesn't have to, it does the address translation at hardware level. And it only comes in when a trap or an exception is raised by the hardware that something bad is going on, and then the trap handler will come into picture. So yeah, this was just an example. Hope that makes things slightly clear, and that also tells you how this is actually an extension of the limited directed execution part, that we are still executing the program on the processor directly, and still performing these kind of address translations such that the actual physical addresses are transparent to the process. Okay, so yeah, I've taken slightly more time, but any quick questions about this? Okay, if not, then thank you all for coming and see you on Monday. No questions, right? Okay, good. See you on Monday. Thank you.